Good evening. So this week we're going to start talking about more in assembly language. By the end of this week, you should all be able to write any kinds of algorithm with PLP-CPU. That's my goal after 4 weeks of CBS. Right? So you should have all the tools you need to write an algorithm. Algorithm, not solve all problems, just algorithms with PLP-CPU. Right? So you have function calls, whatever. And today, we're going to talk more about logical operations. So I've updated the website with a few things. Like if you haven't read about stacks and queues, this is a pretty good document. And if somebody wants to argue why we should start indexing stuff at 1, let's read this. Somebody will bring it up. I'll talk about it later. Why we index from 0. It's actually a pretty interesting discussion. Why we index things from 0. And it's a long history. Computer scientists discuss this, and I think we should index from 0. It just makes sense and makes things convenient. Anyways, so everything is up here. I'll put up lab 2 tomorrow morning. It'll be a fun exercise. Fun. So today, so before we talked about function calls and the stack. Why function calls? Anybody answer me? Why do we use
save code?
Save space for the code. Anything else? So you save program memory, right? Because some code that you use repeatedly, you don't have to inline it on your code every time. You just write it once, just call it. Is there any other advantage of using function calls as opposed to just inlining all your code?
You don't have to type it all out.
You don't have to type it all out, yes.
Space.
Sure. Space, we already said space.
Looks nicer.
Looks nicer. Organized.
From anywhere.
Call from everywhere. So last thing.
Use programs all the time. You can pass values. You can pass.
Well, passing values is a characteristic of a function, right? But why do we use a function? What did you say? Somebody said share.
Yeah.
How? Libraries. With function calls, you can expose libraries, but you don't have to expose your code. Just tell the users, hey, I have this function, it's called this,
Oh, yeah.
and it takes these arguments and it'll return this value. You don't have to worry about anything else. Because without functions, what do you need to do?
Share the whole code, and then everybody's got
Copy
it.
paste, all right? So if you have multiple programs sharing the same code, you can just have one library. That's something we'll talk about later in the semester when you talk about operating systems. How about the stack? Why do we use the stack? We just need a memory access method that what? Because without stack, how would you temporarily store stuff? Have a bunch of variables, right? With a bunch of variables, you have to keep track of all these memory addresses where to put stuff. Something that you only use temporarily. Make sense? With a stack, what do you need? Just one point, start putting stuff, pull them up, right? You don't have to remember locations. You just have to make sure that what's the golden rule of using a stack?
Pull out as much as you put in.
Pull out as many as you put in. What happens if you don't? What if you put in more than you put out? Stack overflow. What if you pull out more than you put in? Stack underflow, where it just rolls over and starts clobbering stuff on the other end. Any questions on functions and stacks? Oh, one more thing. What does stack allow you to do in relation to function calls?
Function in a function.
Return
function in a 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 function. So you can chain functions, right? And this is a very, very common thing to do, especially in your desktops or high-level computers, because it's just made up of programs calling functions, function calling function, and these functions calling other functions. Make sense? Pretty good? And in the lab, you'll see this week how they can be utilized. Now today, we are going to talk about logical operations and shift operations. So I asked before whether you still remember your logic gates from Pre-Science 1 or programming class. In PLP CPU, you only have 3 logical operations: and, or, and nor. So the reason we have nor is because why not? Because we can implement a not with a nor. How do you implement an inversion with a nor? Let's say you have the value a, and you want to do not a. How do you do it with a nor? Nor it with what?
With itself.
With what?
With itself.
No. With nor. So nor is only 0 and 1. When both are 0. It's the inverse of not of n. It'll only be 1 if both are 0, sorry. It'll be 0 otherwise. So if one of the inputs is always 0, then the result will be an inversion of the other input. So that's how you invert a bit with nor. So just nor it with 0. And that's how you do a not operation in PLP CPU. The reason we don't have a not because we want to simplify the CPU, like I told you before. Because when you go to compart and design the PLP CPU, you'll see what it takes to add instructions onto the CPU programming language. If you go to computer architecture, you'll see this. So logical operations are bitwise. Can anybody take a guess what it means? And how is it different with arithmetic that we've seen before, like adding and subtracting? What does bitwise mean?
Just comparisons?
Comparisons between what?
Bits.
Bits. Right? So the operation is independent of other bits. So if you have 2 operands, 8-bit operands, when you do a bitwise operation, each bit of the operand gets operated independently of each other. So or and not are the basic gates that you can use to implement all kinds of logical expressions. That's all you need. Are those the only combination? Is that the only combination of logic gates? No, there are other logic gates you can use to implement all Boolean expressions. But with or and not, you can do it too. So logical operations, first you do to check certain things. Let's say you have 2 switches on your controller, and you want to make sure that both are set. What kind of logical operation do you use? And. If that is 1, and if that is 1, then do this. Otherwise, do this. Make sense? So for those, you need logical operations. Setting, clearing, and masking bits. You can also do some arithmetic with logical operations. So this is what nerds do. Using something that's available and try to do something else in a better fashion. So there are tricks that you can do with logical operations where you use it to do arithmetic operations. Modulo is one of them. Modulo or modulus. So let's look at bit setting. So let's say in register 1, we just look at the bottom 8 bits, and we want to set bit 1. So that's the second bit. Like I said before, we index from the 0th location. So you can do this with the OR-I instruction. The OR-I instruction ORs the register of the second operand, which is this guy with this literal value. In PLP assembly, you can use the 0B prefix to denote a binary representation. How do you denote a hexadecimal? 0x, right? That's typical. In some other assembly languages, this might not be the case. So if you have to write for other architectures, make sure you look up the documentation and see how you write down your literals. Literal is just a value. There's a difference between literal and a pointer. A pointer means this is not the literal value. I'm just pointing it that way. In the context of PLP CPU, it's used in load word store. Right? Literal just means this is it, use it. So what do you think will happen if we execute this instruction? What will happen to the value in register 1?
0, 0, 0, 0, 0, 0, 1, 0.
No.
Just flip bit 2 on.
Oh.
Yeah, bit 1.
Yeah, okay, we'll just flip and leave the other ones there.
So when you use this literal, if you leave the zeros, it'll chop off it'll put 0 for the leading bits, right? So this is actually a 16-bit value, right? Because it's an immediate. So the leading bits will be all zeros. So when you do this operation, you're just setting that second bit 1. Make sense? Now, what if you want to do a logical operation between 2 registers? So this is the I type. You have the immediate value, the immediate literal. Like if you want to do an operation with 2 registers, you just use the OR instruction. Like almost all the other instructions, the first one is your target destination register. The next 2 are your sources. So here you pull a value from register 1, you pull a value from register 2, and OR them together. What will happen after you execute this instruction? So bits 4 and 5 will be set because they were 0, and you ORed with 1, so they'll become 1. What if one of these bits are already 1? It will what? It will stay as 1. Yes?
What's the difference between OR and ORI again?
Or I.
For I.
Or I, it takes a literal value as your second operand. So you get the value immediately here in the program. With OR, you give it the second source register.
Okay.
So in case you get this value from other function and you want to use it, so this value will be generated dynamically while the program executes, right? With RI, the value is static. You give it when you write a program. We'll talk about static and dynamic in a program execution later on.
All right.
Any questions so far? That's how you set bits. In some architectures, you have dedicated bit set instructions. For example, on a PIC microcontroller, you have the BSF instruction. That stands for bit set file. So you give it the memory location and the bit position where you want to set. So in PLP CPU, you have to use the OR instructions, which does the same thing. Why complicate the CPU with a set instruction when you already have something that can take its place? Any question?
There's no way with the ORI to set the upper 4 bits, right?
No, only up to the 16th bit, because the immediate value is 16 bits. You have to use the OR to actually manipulate the top 16 bits. It's a very good question. Because you remember, all instructions are 32 bits, right? And for I type, it needs 16 bits just to tell the CPU what to do and which registers to use. So you're left with 16 bits just for the literal value. You don't have that limitation with OR because the registers are all what? Full width, 32 bits. Any other question?
So you said the third spot in for the register is actually setting the value, you get the value from that spot, register 2, you get the value.
Yes.
And the first two register 1s indicate,
Wait. The first register you list here is the destination of the
destination.
the result. Yeah.
Okay.
These two are the operands.
Okay.
Right. Well, not the operands, the source. All three are operands. So in assembly language terms, the first one is the opcode, the operation code, and whatever arguments you give it is the operands. That's just a term. But in the context of the registers, this is the destination, these two are the sources. Any other question? Now you can set bits and do OR operation. What if you want to clear bits? How do you clear bits with logical operations?
And zeros.
And with 0, why? What happens when you AND something to 0? It always goes to 0, yes. So for example, here, AND-I, similar to OR-I, but just different operation. You want to clear the third bit, the bit 2. Boom. If you want to use the R-type, so you just give it the second register, the clear bit 6. That's it. Bit setting and clearing. When you work with other architecture, if you use MIPS architecture, it will be like this, exactly. But if you use other architecture like PIC or Motorola, it will be similar. You can always use logical operations to set and clear bits. It's actually pretty neat. Why? Because you can set and clear on multiple locations. When you have to run even in C, you still have to do this. And when you optimize things like this and you remember that you can do this, you'll feel so proud. Hey, I just need one instruction to do this. Boom. And nobody else cares. All right. So now we've set and cleared bits. There are other terms where you clear multiple bits, but you don't care about those bits. It's called masking. Right? Sometimes you have a value, and you're just interested in some locations, not the whole word. Right? This is called masking. So what you do, let's say the first one is your data, right? And you're only interested in bits 0, 1, 2, and bits 6. So what you do, you give it a mask. So the mask, everything that is ended with a 0 bits will be clear. Everything that's ended with 1 will be passed through. Does that make sense? So in bit clearing, you're clearing bits because you want to make them 0. In bit masking, you clear them because you don't care about them, and you just care about the bits that you left through. Does that make sense? Can you think of a use case for this?
Yeah, switches like we did in the lab.
Exactly. I'm going to make you work. So we have 8 switches, right? So write a program that lights up LED 0 and 4 if the corresponding switches are cleared. So take 5 to 10 minutes, and let's see who can do this in the least amount of instructions. So if you have a laptop, you can bring it and run PLP2 on it. So whenever we do this, we can actually simulate. So start browsing Reddit on it. Two more minutes. All right. Let's see. How do we do this? What's the first thing we do?
The switches, LEDs.
So we get the pointers to switch LEDs, right? Let's store it in our safe inquiries. What is this one? Switches. Cool. Now, since we're only interested in certain bits, what else do we need? A what? To isolate those two switches. It's just a slide before.
All right.
A mask, right? We did a mask somewhere. So let's put our mask in a register. So what is our mask for this specific example? What did you put as your mask?
51010.
5 ones?
No, it'd be 001, 001. So just being 0 and being 4, half of them.
That's
Four
cool.
ones.
So we want these two. We want these 2 bits, right?
Yeah.
So these need to be cleared. So 0001, 0001, right? So 3 zeros. And since PLP2 will ignore the leading zeros, you can just do. Did everybody get that? So this is the mask for the LED 0, and this is the mask for LED 4. Cool. So this is our mask. And we have our loop. For good fun, man. You'll never forget. Right? So this is your while one forever, right? 3 minutes forever. Now, what do we do?
You can find out what the switches are.
We did.
Load word.
Load word. We actually get the value from the switches, right? So load word, let's use temporary 0. And which one is the switches? Where does it start? S0. I'm using the convention that I mentioned last Wednesday. So safe temporaries is S, and temporaries are 0, are T's. So in our PLP library, like we have a software library, the T registers will be clobbered if the function uses it. S's will not. So on the PLP CPU team, when you program, make sure you have a convention with your registers. Like let's say Charles is writing a function that clobber T0 to T5. Whoever uses that function, make sure you do not use those registers, or you do what? You put them on the stack before you call the function, and then pop them in reverse order. Cool? So after we load the switches, what do we do? Remember, we want to set the LEDs when the switches are clear, right? So what do we do?
And
We want to invert it first, right? So we want to invert all the values with NOR. Because if we end it first and we invert it, then it changes all the values. So we want to invert first before we end it. So one way to write an algorithm is to, well, the first thing is make sure the sequence is correct to get the right value, right? So in the lab, when you try to run your program, first you write down the algorithm in English, like list of operations, and then you translate it into pseudocode or assembly directly. Make sense? Or you can do flowchart. Flowchart is much easier to follow. Like if you want to show somebody else, hey, this is what my program does, and if you just show him the code, especially assembly code, he'll just take your whatever you gave it to him and just throw it in the ground. Really can't read that. So make sure either you have your algorithm explained or a flowchart, which is really clear. Well, should be clear, because you can still make a bad flowchart, but should be better than your assembly. So now we want to invert T0. So we NOR it with 0 register. So that inverts all the bits in that register. What's next? End it. Right. Now you want to apply the mask and mask off the bits that you don't want to use. So you end it with what? Where's the mask?
T2.
S2. Right. So you pull T0, end it with S2, and start back to T0. And the final step is what? You're done processing. You're done computing. What do? Start back, right? Start back to the I/O. Now, different I/O, which is the LEDs in ADSMall. Cool? Any question? Did I screw up somewhere? Probably. Let's run this and see if it works. So let's bring up our switches, our LEDs. Let's start the program. So load word from the switch, NOR it. Boom. So it only shows positions 0 and 4. And because they are cleared, then they light up. Now, if we run this program continuously, it inverts the switch. And you see the rest of the switches are masked off and they don't matter. So I was just going to illustrate the point where with masking, you can do this. And this happens a lot when you try to interface with I/O devices, with their registers. Sometimes you just want to get 4 bits out of the register and not mess with the others. So that's what you do. You put in.
The user has a whole keyboard, and it's a yes/no question. You just mask off every other key.
Yeah.
Okay.
We're just done in a high level where you just give 2 buttons, right? You can even use the keyboard. Yes, no. And sometimes, somehow, the users will break it. It's just statistics, right? You may make like you think a foolproof system. When you have 10 million users, somebody will break it, you know? So any question? Did you see the masking clearly? So the switches and LEDs are really, it's an example where you can see it clearly that things are being masked, just with that one instruction of the AND. You want to change the mask and see what happens?
Sure.
All right. So let's change our mask. The bottom 5 switches now matter. These 3 don't matter. If you change this, they actually get output. Any question?
I thought the LEDs were just, okay, yeah, never mind. Yeah, no. It's HG.
Just change the mask. So now we.
I saw you change the mask, but I didn't see, I thought the switches, I thought the first 5 were
Or
off
clear.
right now, yeah.
On the and statement,
Mm-hmm.
could you make the target S1?
No. What does S1 contain?
LEDs.
Switches.
The pointer to the LED.
Oh, that's right.
Right? If you,
I got
you know, want to see what happens when you do it?
Sure.
Nothing will happen. Because it'll just point to some memory location doesn't care, right? But see, this thing that's the thing with the CPU. Like you with the machine code, assembly language, you mess it up, oh, the CPU will go with it. Fine, you know, go ahead. It's not sentient. Yeah.
Find a way to break the simulator.
I did this morning. When I tried to write this program, the NOR was broken because of something I did over the summer. So I fixed it. I'll put up a new version so you guys don't have the same broken, because this is the development version, and you guys the first one to use it. Sorry.
Oh, this is so much better than that other thing that everybody used before.
Texas? Well, the idea is like we don't just want to write a simulator. We want to have lists of concepts and have a software that support it. Sure. Yes, Jason.
Will we get credit for testing this as testers?
What do you mean?
Whenever you get it done, we all get listed somewhere as
Yes, as a contributor. Everybody. If you look at the contributor list, like students of this class, and I have a picture.
Nice.
This is not a nice thing to do, right? Students are our beta testers. It's always been better. The thing is, like, we even used to collect data on the students, but not this semester. We only do your reflections, which I will put up soon, but that's it. That's the life of a scientist. You know? Can you collect data? Why not? Why don't you? To improve things, not just for the sake of it. You know? Any question? Look at that Raymond Luke looking at his job, doing his job.
Hey, Ren.
Yeah, that's my rapper name.
Any question on masking, bit clearing, bit setting? Oh, every time you have to deal with microcontrollers, you'll see this. And don't do it like people who are obviously have not learned this, where you just assign variables. Oh, no. Even when you program in C, when I see students, like when they're setting bits, they have like OR operations and ANDs, like they go, yes, this guy knows what's up underneath. Because if you don't know this, and you want to set up some registers in C for your controller, you'll start assigning variables, right? And with the OR, with like an ANDing and ORing, like when you set in clear bits, you can combine them all together. So if you look at all this library code that the vendors created, that's how they do it. So if you want to set options for this I/O device, you have this or this or this, and set this and this and this. It makes it look nicer too in higher level language. You don't see this in Java because there's no point. Right? It's object oriented, everything is so verbose, everything has to have a function, private, public, whatever. But when you do low level, you interface directly with the registers. And each bit may mean something. Yes, Charles.
Pull values from two different masks, have two separate masks, pull values from both and have it together.
Yeah. Make sure you have the right sequence. No question? No other question? So I looked up, the class is listed till 8:45, but this is a special case because we have, it's actually a 2-class plus lab, right? So it actually is a 15-minute class. So the class due at 8:20, not 8:45. Unless you want to go to 8:45, I'm open to that. I just lifted all the hands. So next time we start talking about, oh, by the way, awesome people use zero index. That's all the argument you need. Like, what do you use one index? We come from one, right? Oh, well, yeah, but you suck. Right? So, even Professor Dijkstra said,
if everybody did a zero index, that'd be fine. But you run into like certain codes that they start at 0, certain things they start at 1, and that's where it gets confusing. If you always count on zero index,
you should always count from zero index. Otherwise, you're wrong. You say that. If you say like somebody counting starts from 1 from this like program, let's start modifying your code. Just kidding. Make sure you consult your team leader. All right. I'll see you all Wednesday. I'll put up the lab description tomorrow morning.
Do we have homework?
For next week.
Eat out of the locker.
Not for tomorrow. Oh, team contracts.
You want us to